So this is week 3. It's going to be a weird week and kind of a short week because of Thanksgiving. So that's why I wanted to get us going on it early. This week we're still doing measures of variation. Only last week we concentrated on kind of the grand poobah of measures of variation, the standard deviation. That's what everybody's most familiar with, and that's the most common measure of variation. I think we also talked a little bit about the range, which is widely used and understood. And then there are the kind of the B team measures of dispersion, the percentiles, which are very important and they can tell you a lot, but the only reason why they're the B team is because they aren't used as widely and they aren't as widely known, probably because they're not used as much. But a percentile is very simply just a score that designates a cutoff where a certain percentage of your data is equal or less than that. Now, sometimes percentiles are reported as strictly greater than, and sometimes it's, equal or less than. So what I mean is, like if you're talking about, oh, so-and-so scored in the 90th percentile on a test, and the 90th percentile score for that test, let's say, was, 82. Some sources would mean that if you scored an 82 or below, if you took all of the scores on the test and you added all of them up, including all of the 82s, that would be 90% of them, because I think I said that was the 90th percentile. So let's say I said the 90th percentile. Then that means 90% of the scores would be 82 or less. Other sources, when they say 82 is the 90th percentile, that means 82 was strictly better than 90% of the scores. So you would add up everything only up to 81, and all of those would account for 90% of your data. So it just depends on which way it's used. It's most commonly used as a strictly greater than. So it means that 90% of the things are less than this value, whatever that value happens to be. So for example, if you're in the 60th percentile for height, then you are taller. See how it says taller, strictly taller, not taller or equal than 60% of all individuals. Okay, and percentiles are really just a way of, like I said, showing the spread of your data, but really the most important use of percentiles is allowing you to compare two different sets of data that are possibly on two different scales. And the most common example of that would be the SAT scores and the ACT scores. Now, depending on where you live in the country, you tend to take one or the other. I don't know why, but they seem to be geographical. The West Coast tends to take SATs more, and the East Coast tends to take ACTs more. But there's a mix. I mean, you could live in California and take the ACT. You could take both, right? Both of them are basically standardized tests to get you into college. Well, they don't get you into college. They're a standardized test that helps colleges evaluate whether or not they think you're going to be a good student, whether or not they're going to let you in, right? It's one of several things that they look at usually. But in any case, they're on two completely different scales, right? The SAT, in fact, the SATs have changed throughout the years. They used to be out of 1,600. Then they went up to 2,400. Then I believe they went down to, I think, like 2,000 at one point. And now I don't know where the hell they are. They keep, because before it used to just be math and English, and it was 800 points for math and 800 points for English. Thus, you could get a maximum of 1,600. Then they added like a writing component where you had to write some essays, and that was worth another 800 points. And then it went up to 2,400. And then I think they decided that component shouldn't be equally weighted, so they weighted it less, and then it came down to like 22 or 2,000. I don't know. But in any case, it was on a pretty big scale, whereas the ACT has always been on a scale of like 45 or something like that, some weird number. It's not even, it's not even 100. It's just like a perfect score is like a 42 or something strange like that. So it would make no sense to, have two students apply to a college and one person has an ACT score of, let's say, 32, and then the other student has an SAT score of, let's say, 1500 on the old version that went out of 1800 points. And the admissions people would be like, well, which one's better, right? And that's where percentiles come into play, because your score on both of those tests would be listed. They would give you the raw score, right? So you would say, okay, I got a 1500 on the SAT, but then it would also say that score puts me in the 87th percentile, which means I scored better than 87% of all the students who took that SAT. And by the way, it's that specific SAT because, there are different SATs and different ones are considered harder than others, right? So that's, again, why they do percentiles, because even one SAT to another SAT are different depending on how hard the questions are. And then the ACT student comes along with their score of 32, and it says, score of 32, 90th percentile. And you go, aha, now I know this student did better because, they were in a higher percentile for their test, right? So that's one of the main uses for percentiles, is it lets you compare two different sets of data that are on two different measurement scales. Some of the most common percentages out there is the empirical rule that you may have heard of. And that is the 68, 95, 99.7. Now, these are rough approximations. They're pretty close, but they're not perfectly accurate. And what it says is, if you have a set of data that is normally distributed, and it only works with things that are normally distributed, by the way, then if you have a normally distributed set of data, i.e. it's got that pretty little, symmetrical bell curve, then 68% of your data values are going to be within one standard deviation of the mean. So wherever the mean is, if you go one standard deviation in both directions, that interval will contain 68% of your data. If, however, you start the mean and you go out 2 standard deviations in both directions, whatever that interval is, that will contain 95% of your data. And then if you go 3 standard deviations in both directions, that will contain 99.7, or damn near all of your data. So here's a simple example, right? If you have a mean of 40 and a standard deviation of 3, we can figure out what range would encompass about 68 and what would get 95, and so on and so forth. And the best thing to do with these questions is to draw a picture. Always draw a picture, right? So you draw yourself a simple little bell curve. The mean is always in the middle, right? So right smack dab in the middle is your mean, X bar. And so in this case, it was at a 40. You always, your distribution is sitting on the number line, right? So this is a number line, right? So this is 40, and you go all the way down here to 0, right? And that would be your y-axis, right? If you remember your geometry at all, your Cartesian plane, right? And then you go in this direction, it's negatives in that direction. All right. So this is sitting on the number line, centered at 40. And then the standard deviation is 3. So if we go out here, right, to 43 and go down here, the same distance, right, to 37, then that's 68% of your data. Then if we go out another 3, so 46, 34, right? So all of this from here to here, that's 95% of your data. And then if we go all 3 more out there, right? So we go down to 31 and up to 49. That's 99.7% of your data. So that means these tails have almost nothing, right? I mean, it's 0.3% total. And since it's symmetrical, that's half, right? So it's 0.15%. Now that's not 15%, that's 0.15, right? That's 15th of a percent, right? That's less than 1%. So 0.15% in each tail. Teeny tiny bit in the tails, right? So that tells you one thing, that the vast majority of all of your data is within 3 standard deviations in both directions. Okay, questions at all on the empirical rule? Okay. Now, the empirical rule doesn't require that your data hold to this pattern. It just tells you what to expect if your data has a certain shape, i.e. is normally distributed, right? So it's not like you can force these percentages on your data. This is just a rule that only applies to normally distributed data. And so when you have that normally distributed data, you can calculate these things this way. Well, here is a visual representation of some of these measures of spread that we're talking about, i.e. percentages, percentiles. Only now we're going to look at some very specific percentiles. We're going to call them quartiles because quarter, is 25%. Quartile is, Latin for a quarter or 25%. So the lower quartile just represents the cutoff that has 25% of your data below it. The median we already know is where half your data is below it, i.e. 50%, and that's actually Q2, the second quartile, right? Because 25 plus 25 is 50, so that's why that's the second quartile. And then the upper quartile is Q3, i.e. 25, 25, 25, that's the 75 percentile, right? So the 25th percentile, the 50th percentile, the 75th percentile, they all mean the same thing as Q1, Q2, Q3, or lower quartile, median, upper quartile, right? It's 3 different ways to describe the same 3 things. You could call it a lower quartile, you could call it Q1, or you could call it the 20th percentile. Same damn thing. Basically, just make sure that you understand that Q1 has the cutoff for 25% of data is below it, right? Q2 has 50% of the data below it, and Q3 has 75% of the data below it. And then when you make a regular box plot, not a modified box plot, but just a regular box plot, the whisker, these are called box and whiskers usually. Sometimes they call them tails if they don't call it a box and whisker plot, right? They just call it a box plot. But in any case, these little wings, the little tails, the little whiskers, whatever you want to call them, the one on the left always stops at the minimum value of your data set. And the one on the right stops at the maximum value, right? Highest value, lowest value. That's if it's just a regular old box plot. If it's a modified box plot, what they do is the tails stop at the smallest value and the largest value that is not considered an outlier. And then the outliers are represented by asterisks or dots or whatever, right? And when you have outliers, it shows you that your data is skewed. When you have a box plot that's fairly symmetrical, right? You can see that this tail is pretty much the same length as this tail, and the median is pretty much right in the middle. Then you know you have a fairly normal distribution, right? So these box plots can tell you the overall shape of your distribution just by looking at them. Once again, you can visualize the percentiles by looking at how they relate to these standard deviation. This is the Greek letter sigma, which stands for standard deviation of the population. Mu, right, is the mean of the population. When we're dealing with samples, we would use X bar for mean and then a little lowercase s for our sample. But here they're just talking about it if it was in a population. Well, we know, remember, that if we went 1 standard deviation in both directions, that's 68% of our data, which means it's 34% in both directions, right? 68 divided by 2, 34 here, 34 there. So we can see the box, right? Remember the middle, the line right in the middle of the box is Q2, which has 50% of our data below and 50% of our data above. Normal curves are perfectly symmetrical, right? The mean is right in the middle. The mean and the median are the exact same thing when you have a normal distribution. So exactly 50% of your data is above the mean and exactly 50% of the data is below the mean. So the Q2, the median, sits here and lands right on the mean. It lines up on the mean. And then if we go out 25%, right? Because if we go down 25%, then there's 25% below it, right? Remember, this is 50. And if we go up 25%, there's 25% above it. And we can see that that's where 75 is, right? So here's 25, 25, 25. So we can see here's 70, here's 50, Here's 25. That's Q1, Q2, and Q3. And we can see that that box, this little inner box piece, is a little bit narrower than one standard deviation in both directions. Because remember, one standard deviation in both directions gives us 68%, but the box only gives us 50, right? Because if this has got 25% below it, and this has 75% below it, then this has 50% within the box. So that's why these lines, right, they stop here and here, shy of where the where the standard deviations are, because they go all the way out to 34% in each direction, whereas this just goes 25. So it's just kind of a visual representation of how a box plot would line up with a nice, pretty little normal curve. And when it's normal like this, you don't have any outliers. So when something's perfectly normal or very, very close to normal, you don't have outliers. So the tails are going to go all the way out to the ends of the curve. Okay, scatter plot is another kind of visual, graph kind of thing that we talk about this week. And a scatter plot basically just shows the relationship between two measurements, right? So in this case, we're looking at the price of peaches versus the number of peaches sold. So each dot represents two things, right? This dot represents how many were sold and the price at which they were sold. So you can see that each dot represents two measurements, the thing on the y-axis and the thing on the x-axis, right? So the vertical and the horizontal. And when you plot all these dots, like maybe these prices were taken, over the last 10 years, or maybe they were taken every week for 20 weeks, how many dots there are there, and prices were fluctuating. Every time the price of peaches went down, you sold more, which makes sense, right? People are going to buy more, as it costs less, and as the price goes up, they're going to buy less. And then you plot all these dots, and you get this nice little scatter plot, and you go, oh, you know what? There's a pretty strong relationship between these two things because the dots all seem to line up fairly well in a pattern. It's not super strong, right? They're spread out a bit. This one's definitely stronger. See how these are almost in a perfect straight line. So we can say there's a very strong relationship between temperature and sales of ice cream, which again makes sense, right? The warmer it gets, the more ice cream you're going to buy, and the colder it gets, the less ice cream you're going to buy. So that's basically what scatter plots tell us, is whether or not things have a strong relationship, kind of a moderate relationship, whether it's in the positive direction, right? So this would be a positive correlation, meaning as one thing increases, the other thing also increases. This is a negative correlation because as one thing increases, i.e. as the number of things sold increases, the price goes down, or really vice versa. This really should have been the other way. X should have been the independent and number sold should have been the dependent, because it makes more sense that price is going to drive what's sold and not what is sold is going to drive price, right? The more you sell, you aren't going to just keep lowering the price, right? You set the price first, and then that dictates sales. So it should have been the other way around, right? Temperature affects sales. It wouldn't be the other way around to say, hey, as sales go up, temperature goes up. Like, let's all sell more ice cream because it's so cold. It'll make the weather better, right? It doesn't work that way. So there is really a true kind of independent and dependent variable with these things. Now, if you switch places with them, the correlation is not going to change, right? The pattern is going to look exactly the same. It's just this measurement's going to be on this axis and this measurement's going to be on that axis. So you're going to get the exact same looking graph. You're going to get the exact same, spread. They're going to be just as spread out or just as tightly together. When you calculate your correlation coefficient, if you've heard of that, the R value, that's not going to change. So really the only reason why you would make sure that one was on the X versus on the Y is just for context. It makes more sense to have price of peaches being the X and number sold being the Y. But it's not going to make the numbers wrong. Then you look at things like this and you can see, well, there's kind of a positive trend, right? As high school GPA goes up, looks like college GPA goes up. But you can also see these things are pretty spread out. They're not tightly woven along a straight line. So you could say that the correlation between these two things is even weaker than what we saw before. And then these things, wow, there's like no correlation at all. I mean, they're just all over the place, right? So this is pretty much, so we're looking at months, and then we're looking at number of people. I have no idea what this represents, but obviously there's no correlation, which brings us to visualizing these things, right? Positive correlation, because you can see as we get bigger X values, we're also getting bigger Y values. Negative correlation, because as we're getting positive X values, we're getting smaller Y values. No correlation, just looks like a random buckshot all over the place. So we can get more specific and go, okay, these things are lining up perfectly on a straight line. So that would have an R value of -1. These things are spread out quite a bit, right? So it's getting closer and closer to 0. This is, and you can still see there's a negative trend. So it's -0.3. All over the place, 0. Now there's a positive trend. They're a little tighter together than this one. So it's a 0.4, even tighter still. So a 0.8, and then perfectly, pretty much in a straight line, a 1. So that's what correlation is. Your correlation coefficient, your R value, always ranges from -1 to 1. -1 means they line up perfectly with your model. Now we're always going to be doing linear regression, which means we're looking for straight lines, but you could have things that line up perfectly on a curve. As long as you can define that curve algebraically, then you could still get an R of 1 for things that are non-linear. But for this course, we're only dealing with linear stuff. So it's going to, for our purposes, it's going to be if it's a perfect straight line, it's a -1, or if it's a perfect straight line with a positive slope, it's a +1, those types of things. But I just want you to know that there are other types of correlation you can do where you're not looking for a straight line, you're looking for maybe a parabola or a logarithmic scale or whatever it happens to be. But as long as it fits some perfect curve, then you would still get an R of 1. And then as it spreads out, as it gets wider and wider off of that perfect straight line in the case of this class, or that curve in the case of another example, then it just gets closer and closer to 0, right? So if it's in the positive direction, it goes closer and closer to 0 with positive numbers. If it's in the negative direction, it gets closer and closer to 0 with negative numbers. All right, questions at all on the box plots or correlation? Okay, then the last thing I want to discuss is just to remind you guys of what's happening the next 2 weeks, right? So this mini project technically has 2 parts. The first part is due a week from today, midnight, the end of week 3. And it's where you use the new drug data and you basically just answer a bunch of questions. And you compute a bunch of things, you spit out some outputs, and you discuss what you see. And then the part 2, I wouldn't worry so much about Turnitin. I think there's a Turnitin link. Like when you turn it in, I think it automatically gives you a Turnitin score. But I wouldn't worry about a bad Turnitin score on this, because I'm fairly certain all of you are going to be listing the questions. And when you list the questions, of course, there's going to be a huge similarity because everybody's listing the exact same questions, right? Part 2, however, is you need to go out there and you need to find a research article that has some statistical analyses in it. Ideally, you would find a research article that is based on the topic that you're going to be doing your dissertation on. So you could find an article that would actually be part of your lit review. If you've already done part of your lit review and you already have an article that you've already read that has some statistics in it, then by all means, you can use that again here. Because what you need to do is you need to find that published research article, describe the various elements in it, and post all of that to the doctoral dialogue. And your initial summary of this research article is due Thursday at midnight of week 4, because then that way it gives everybody enough time to read your critique, right, your summary, and then respond to it. And those responses are due by the end of that week. So the replies, right, are due by Sunday of week 4. So that's why this needs to be done by Thursday. So again, try and find an article that means something to you, that that is something to do with your research topic. If you haven't thought that far ahead, you're not even close to thinking about a research topic, then just try and find something that maybe interests you, so that you're not just reading a stupid research article that is a waste of your time, so to speak. Just make sure that it has some statistics in it, and it really should be some quantitative statistics, right? Not just qualitative junk, not just descriptive things where, 12% of our respondents had, blue hair, like things that where they can actually compute a mean and a standard deviation and those kinds of things you can talk about. Okay. But if you can't find those and everything you find is just qualitative, then we can make do, but it's going to make your life a lot easier to answer the questions that they ask you to answer if you've got quantitative results. Okay, questions on the mini project. All right, well, that's it. That's all I got. I mean, it's a pretty short one this week. So I'll open the floor to, do you have any homework questions? Anything you can even ask about, week 2, which is due here in a few hours. Nothing? No questions?
No, I don't have any questions, but you did clear up some things for me, especially from a conversation I had with my assistant Sue. And what we talked about was the way percentages are used. People will really confuse you that 82 percentile or 82% score or 82 score on a test makes a whole lot of sense, because he was saying the same thing. I was not getting it. I was not understanding what he was saying. And so that makes a whole lot of sense, because people can skew the data by saying, well, they were in the top 10 percentile.
Yeah.
And it makes, the way you explained it makes a whole lot more sense.
Good. I'm glad it helps. Anybody else? Christina?
Yeah, I do have a question. So when you're reporting frequencies, and I just was curious about a preference that you would have on the graph. This is actually in the mini project. But like, for example, when you run a frequency table for like a categorical variable, you will have some counts where there's no like category recorded. Like that happens actually in the assignment.
Sure.
Do you want us to graph that value?
Well, when your histogram should it should have,
okay.
Well, it depends on if you're talking about discrete things where, there's like 8 things and you're counting how many are in those 8 different things, then yeah, you would definitely show all 8, even if one of them had a frequency of 0. So you would just have no bar there. But if you're talking about continuous, well, even with continuous data, if you had classes and one of your class had a value of 0, yeah, it's valid. You're showing that there's just nothing in that category.
Okay, I just was curious, because actually in SAS you can select to show it or not. And I did select to show it, just because, like I said, like the data old study part of me, like you would never leave that out. Like even if it wasn't reported, it doesn't mean that there wasn't data collected. It just didn't have a category reported, but you don't necessarily throw that out.
Right. Yeah. I'm of the same old school. I don't throw anything out unless I know for sure that it's false data.
Okay. Got it. Okay. That was my question. That was the one I couldn't remember the other night, actually. I knew I had something and I couldn't remember.
Good. Anybody else? All right. Well, I guess we can end early. You guys can enjoy the rest of your Sunday. We will be meeting again, remember, Wednesday, because of the Thursday holiday. And hopefully I can answer any and all questions you will have at that point for the week 3 stuff. So just remember that next week, and it sucks that it falls on Thanksgiving week, that you have 2 things due on the same week. You've got the homework set for next week and the mini project, which is why I kept trying to get you guys started on the mini project, as early as possible this week, so you'd have less stuff next week. But that's what you got to do.
One other question, Dr. McBride, are we able to turn the homework in on Friday early? I thought you meant, I know the mini project, no, but the homework, yes, no?
No, I'm not gonna have time to look at it. Sorry.
Got it. That's okay. Thanks.
What if we turn it in tonight? Still no?
Week 3?
Yes.
Tell you what, if you turn in week 3 by Wednesday morning at 9 a.m. my time, so Wednesday at noon, I will look it over and get it back to you before we have our meeting Wednesday night.
Perfect. Thanks so much for that.
Perfect. Yep. All right. Thank you. That's great. Thank you.
Yep. Anything else? All right. I will hopefully see you guys Wednesday.
Thank you. Have a
Yep.
good night.
You too.
Thanks,